Good morning. So in this talk, I'm going to talk about SPANStore, which is designed for minimizing cost for using cloud storage. So this is a joint work with my lab mates Michael and Dorian and our advisor Harsha, and Professor Ethan from USC. So as we all know, the common technique for application to deliver a good performance is to build geo-distributed service. So now a user can be served within their closest data center and have a low latency. But not all companies can afford to build their own data center. That problem can be solved by using cloud service. So today, many cloud providers have offered their services in many locations. For example, Amazon has their cloud services in 8 of its data centers. But even with the support of a cloud, things are still not easy. So data can be viewed or changed by users from different locations. For example, in Facebook, a user's post can be read by his friends from other countries, or in Dropbox, a file can be shared by users from different locations. So this means that not only the application, but also data needs to be geo-replicated. But today, cloud provider only provides isolated pool of storage in each of its data centers. So this requires that when application make a request, it needs to specify which data center to use. So it makes that the replication is left to individual application. So the problem of enabling geo-replication is certainly not a new problem. There has been a lot of recent work focusing on either achieving a faster performance or stronger consistency. But when the application is built on cloud, in addition to these two goals, there is another consideration that is also important, which is minimizing the cost. So driven by this motivation, we designed SPANStore. So in the rest of my talk, I'll first give a brief overview about how does SPANStore work. And then I'll talk about several techniques for reducing the cost. And then on the last, I'll show some evaluation results. So SPANStore is a unified view key-value store spanning cloud storage services with a simple put-get interface. So our main goal is to minimize cost while satisfying applications requirements. So such requirements include the latency SLOs. This is a latency bound on each request. For example, the 90th percentile latency should be finished within 100 milliseconds. Consistency. So currently, SPANStore provides two consistency models for applications to choose. So eventual consistency and per key sequential consistency. So the third requirement is default tolerance. It states that how many failures should SPANStore be able to tolerate. So to use SPANStore instances need to be set up. And an application is linked to a SPANStore library. And when the application wants to fetch or store data, it sends a request to the library. And the library will first look at the metadata in the SPANStore instance. So metadata indicates where to fetch or store the data. And it is generated based on the cost-effective replication policy. And then the library will issue the request accordingly, and upon receiving responses, it will return the data or the acknowledgement back to the application. So in each data center whose storage is used by SPANStore, there are SPANStore instances. An application can be deployed on all or subset of these data centers. So to find the cost-optimal replication policy, SPANStore also runs a central placement manager. So the time in SPANStore is divided into a fixed duration epoch. So at the beginning of each epoch, the placement manager needs to determine what is the optimal replication policy to use in that epoch. So in order to find such replication policy, the placement manager takes two types of static input. The first is the SPANStore characterization, which includes the inner data center latency and the pricing policies. The second input is the application requirements. So in addition to static input, there's also another dynamic input. So the placement manager needs to gather the workload information from all SPANStore instances. And by jointly consider all this information, the placement manager will judiciously determine what is the cost-effective replication policy, and then send the replication policy back to all the SPANStore instances. So now the question is, how can the placement manager find the optimal replication policy? So next, I'm going to talk about several techniques in enable SPANStore to further reduce the cost. So in geo-replication, fundamentally, there are two questions need to be answered. So for each object, where to store the replica and how to execute puts and gets. So in terms of minimizing cost, why these are hard problems? So why can't we just go ahead and pick a data center with the cheapest storage price and store data there? So it turns out that the cost for using cloud storage is not only based on the amount of data that is stored. It also includes the request cost, which is based on the number of requests issued, and the data transfer cost, which is based on the amount of data transferred out of the data center. So combining all three costs, we get the storage service cost. So in order to find how to replicate the data with a minimum cost, we need to jointly consider all these three costs. But first, we found that to determine the location of each replica, it is largely affected by the latency SLOs. So for example, let's consider the following scenarios. So we have a request of the same object from 4 different data centers. So if the latency SLO is low, it's likely that you have to store data on each of these data centers. So this is because the cloud provider tends to build a minimum number of data centers with the widest area covered. And the 2 data centers in the same cloud tend to be distant. So let's see. So let me show you a measurement we did on Amazon data center. So in this measurement, we want to say on each data center, how many other data centers can be reached within a certain latency bound. So in this graph, each bar indicates one Amazon data center, and the y-axis is the number of data centers within a certain latency bound. And the latency bound here we choose is 100 milliseconds. So from this graph, we can see that. So for most of the data center, there are no other data center can be reached within the 100 millisecond latency bound. So this indicates that if the latency SLO is low, it's likely that you have to store a copy of data everywhere, and it results in very high replication. So in order to reduce this high replication, we probably want some data centers in between of those data centers that holding the replica. But we cannot just go ahead and tell the cloud providers to build more data centers. But we're noticing that the different cloud provider may have data centers in different locations. Therefore, we decided to deploy SPANStore across multiple clouds to achieve the goal. And notice that the different cloud providers notice that different cloud providers all provides a simple put-getter interface. So this will also make our implementation easier. And we did the same measurement, but now we're using 3 clouds. We use Amazon S3, we use Windows Azure, and Google Cloud Storage. And we see that now within a 100 millisecond latency bound, there are more data centers. So by leveraging the denser data center location, we can potentially reduce the number of replicas and meeting the latency SLOs. And there is also an added bonus of using multiple clouds, which is the price discrepancies. So here I'm showing a table of prices of 3 data centers from 3 different clouds. And each column contains the price of one dimension of the storage price. And from the table, we can see that there are variabilities almost in all dimensions. And if we point out what is the cheapest price in each column, we can say that there's no data center that has the cheapest price on all dimensions. So this means that we can judiciously determine the optimal replication policy, leveraging these price discrepancies to further reduce the cost. But even with the price discrepancy, doing this are still hard. So let me show you an example. So if we have an object that only receives few GET requests, so what is the best way to store it? So the best way is to store it in the data center with the cheapest storage price. But if this object will receive more GET requests, and some of the requests might say very high latency, so violate the latency SLOs. So in order to reduce this high latency, so one thing we can do is to pick a few data centers with a cheap request cost and store the data there. But this will only be cost effective if the object size is small. If the object size is big, this will incur very high data transfer cost. So in order to reduce this high data transfer cost, the best we can do is to store a copy of data on each of the data centers where the request is received. And this will give you 0 data transfer cost for GET, and you get the best latency you can have. But the problem is that if the object size is big, this will incur very high storage cost. And if there are also put requests, some of the put requests might see very high latencies and have high cost. So from the example I just described, so there's no replication policy that is optimal all the time. So the optimal replication policy is critically depends on two things: the application requirements and the workload properties. But for application requirements, it's just a simple static input from the application. So the real challenge here is that how can we estimate the workload? So the simplest way to estimate the workload is just to use object's old workload as a prediction of its future workload. So to see if this is possible, we did analysis on Twitter datasets. The Twitter datasets contains amounts of data with 120,000 users posts. And in this analysis, we measure we measure each user's timeline object's workload. So when user make a post, it will append the post to his timeline as well as all his followers' timeline. And we divide the time into hours, and we try to predict each timeline object's workload based on its workload on the same hour in the previous week. And the x-axis is the prediction error, and the y-axis is the CDF of all analyzed hours. So note that the x-axis is in log scale. And here I'm showing the result of one user's timeline object. So from the graph, we can see that there are really high variabilities. And the 60% of the time, the prediction error is higher than 50%. The 20% time, the prediction error is higher than 100%, and the prediction error can be as high as 1,000%. And this high variabilities exist in all users' timeline, all active users' timeline objects. So we cannot just use an individual object's workload to predict the workload. But there has been observations of diurnal or weekly patterns of aggregate workloads. So we're trying to leverage these properties to predict the workload. But we cannot not just aggregate all objects' workload because different objects may receive requests from different places. So we first classify the object by its access set. So access set is the set of data center from where the object is accessed. And we think this is a reasonable input from applications because the application actually has the knowledge of the sharing patterns of each object. For example, Dropbox knows where the file is shared. And in Facebook, when a user makes a post, Facebook actually controls who the other users to show this post to in their newsfeed. So we did the same analysis on aggregate workload. And from this graph, we can say that aggregate work now is more stable and therefore predictable. So now we have a way to predict workload. Finally, the placement manager has all the information it needs to compute optimal replication policies. So next, I want to talk about how to execute inputs and gets. So when the optimal replication policy is determined, so for get, where to fetch data is also determined. If it's in eventual consistency, you can just get from a data center with the cheap request plus data transfer cost. And if it's a stronger consistency, you might get from more replicas. And where to fetch data is determined by the optimal replication policy. But for put, things are slightly different. Notice that put are always propagating the same copy of the data. So here we use another technique, relay propagation, to further reduce the cost. So here again, we're leveraging the discrepancy of cost of data transfer price. And notice that the data transfer cost in Europe and US is usually cheaper than the data transfer cost in Asia and South America. So when a data is sent from a data center with expensive data transfer price, we can relay the propagation to the data center with a cheaper data transfer price. And for example, here we have a data center in South America and wants to send us 3 copies of data to 3 data centers in Asia and the Pacific. So if this propagation is asynchronous propagation, which means it is not bounded by the latency as allows, we can send the data to the data center with the cheapest data transfer price across all data centers. But if this propagation is synchronous propagation, so doing this might violate latency as allows. So in this case, there might be only few choices that enables cost savings. So in this case, we can only be able to send the data to the data center in Asia and let him to propagate the data. But still, we can see some cost savings. So to sum up, there are 3 insights we use to reduce cost. So we leverage multiple cloud deployments to reduce cost and latencies, and we use aggregate workload predictions to predict workloads, and we use relay propagations to reduce the propagation cost. So now the placement manager will combine all these insights into an integer linear programming problems, and by solving the problem, the placement manager can get what is the cost optimal replication policy. So there are other techniques we use to further optimize the SPANStore. For example, we use metadata management to account for workload change. We use a modified two-phase locking protocol to reduce the computation resource uses for execute inputs. And we use asymmetric quorum sites to meet a flexible latency SLOs. But due to time constraint, I won't talk about them in detail here. So last, I will show some evaluation results. So in the evaluation, we said the application is deployed on Amazon EC2, and we said the SPANStore is deployed across Amazon S3, Azure, and Google Cloud Storage. And the evaluation contains two parts. In the first part, we use simulation to violate the cost savings enabled by SPANStore, and we use the actual deployments to violate that SPANStore can meet latency SLOs. So in the actual deployment, we use SPANStore as a backend storage for two applications. Retweets, which is a Twitter clone, and Share.js, which is a collaborative document editing service. So first, let's talk about simulation. So in the simulation, we compare SPANStore in three scenarios. We compare SPANStore against a replicated ever strategy. We compare SPANStore with a single replica strategy. And also, we compare SPANStore under a multi-cloud deployments and SPANStore under a single cloud deployments. But due to time constraint, I will only show the results for comparison with the replicate everywhere strategy. So in the evaluation, we said application requires per key sequential consistency. And the way we said put SLO and get SLO is follows. So because we want to compare with replicate everywhere strategy and single replica strategy, so we want those two strategies to be included in the solution space of SPANStore. So therefore, we set the put SLO as the SLO that every data center can reach every other data center. So now the replicate everywhere strategy is included in the SLO, included in the SPANStore solution space. And then we set the get SLO is the SLO that every data center can reach a common data center. So now the single replica strategy is included in the SPANStore solution space. And we set the SLO as stringent as possible. And here we compare the cost of using replicate everywhere strategy and the cost of using SPANStore. And the x-axis is the cost ratio, and it is in log scale. And the y-axis is the CDF of all access set. So here we consider several workloads. So for the workloads, we use the big objects receive a lot get requests. So in this workload, this workload requires a lot of data transfer from the replica to the application. So if you remember the example I mentioned earlier, so when an application do a lot of reads, the optimal replication policy is actually replicate data everywhere. Therefore, in this case, we only see a slightly savings by SPANStore, slightly savings by using a relay propagation. So the second workload is a big object receive a lot put request. So this workload requires a lot of data transfer from application to replicas. And so in this case, the replicate everywhere strategy will have really high data transfer cost. So by using SPANStore, you can reduce those part of cost by storing few copies of data. So now look at two workloads with a big object. So now, next, let me show you some workloads with small objects. So the difference with the big object and small object is that when the object size is small, the cost for storing the data and transferring the data can become minor compared with the request cost. So here we can say that by leveraging the discrepancy of get request, there's really high cost savings by using SPANStore. And similarly, if the object receives a lot of get request, the cost savings also from the discrepancy of put request. But the discrepancy of the put request is higher than the discrepancy of get request. Now we see higher saving ratios. So last, let me show you show the operation latency by using SPANStore. So due to time constraint, I'll only show the results for retweets. So we deployed a SPANStore prototype across 3 different clouds, S3, Azure, and Google Cloud Storage. And we run retweets on each EC2 data centers. And we scale down actual Twitter workloads as the workloads input for retweets. So when retweets is running, we measure several operations latency. So when a user makes a release timeline, which is actually a GET request. And when a user make a put, which is actually a put request. And in addition to these operations, when a user make a post, it also will read his follower's timeline and append a post to it, which is actually an insert operation. So note that insert operation is a get followed by a put. So the system requires an eventual consistency, and we said the 90th percentile get put latency is 100 milliseconds. So here's the result of the latency of operations. So the x-axis is the latency, and the y-axis is the CDF of operations. So the green bar here is the 90th percentile latency, and the blue bar here is SLOs. So from the graph, we can see that more than 90% of the put-get request can be finished within the SLO. So note that the insert operation is actually the put plus a get, so the latency of the insert should be 200 milliseconds. So again, here is more than 90% of the insert operation can be finished within the latency SLOs. So in this talk, I present SPANStore, which is a storage service, cloud storage system focusing on minimizing cost while satisfying applications requirements. So we leverage multi-cloud deployments to lower the latency and the cost, and the SPANStore can judiciously determine the replication policy based on the workload information and the application's requirements. So thank you, and I'm happy to take any questions.
Yeah, my name is Christian Cachin from IBM Research. I had a question on the strong consistency model where you're using quorums. Can you comment on where the metadata for these quorums, like timestamps and or sequence numbers, are residing, or they are stored on the cloud or on your trusted gateway?
So for the quorum, there's no timestamp for that. So we use two-phase locking. So when you want to issue a request for put, you just lock the object inside data center. So to protect the concurrent writings of the data.
And how do you lock that?
Sorry, yeah.
Do you lock that inside the data center or on the mediator?
So when you make a put, you will put a lock in the data center. You try to put the object, and so when there's another data center try to put the object, you cannot do it because the object is locked. So the two-phase locking protocol actually protect the concurrent write of the same object.
Okay, thank you.
So there's no timestamp involved.
Let's do a question from the web. What if the compute workload is also distributed on multiple cloud providers? You probably don't want a VM on EC2 to work on data from Azure. So here, that's actually so we're talking about the application also deployed on multiple clouds, right? So here, actually, we didn't consider the cloud, the difference between the cloud from the different cloud providers. So we assume the application always deployed on the same cloud provider. Due to that, actually the effort to make two versions of the applications is harder than just deploy the data across multiple clouds.
Setu from NetApp, and you mentioned that you're creating replicas. So there is also a cost to holding these replicas, and it's like the cost you mentioned, there is a timeline associated with it. It's like 10 cents per gig per month. So do you have a policy for removing replicas?
Yeah, actually, so this is we're focusing on the active data. So if after a while data becomes old and no one accesses, you can just store the data to the storage with the cheapest price. You can use that kind of mechanism to further optimize.
Musa from Stony Brook University. You're using integer linear programming, which is known that is NP-hard. So the size of the problem really matters here. I wanted to see how big the size of the problems you're solving is, and what the overhead it has. What kind of overhead it has, like, in terms of time on your system.
Okay, so first, to solve the integer problem, we use simplex. So we can get the result within a second. And also, because the optimal replication policies is computed from the placement manager, and the placement manager will actually compute the replication policy offline. So it comes to finish propagate the strategy to the SPANStore instances. So it can take a while to compute our replication policies.
So how big was the problem size?
How big the problem size?
Yeah, so integer programming is solving a problem.
Yeah.
Right? So how big is the problem size, like in terms of number of variables and things like that?
Oh. So for So for data centers, there are, now we use 3 clouds, there are like almost 20 data centers. So for each, you can either choose or not choose it. And for each replica from each access set, you can either choose or fetch or doesn't fetch it. So I think, I don't remember exactly the case. So for the access sets with, for the access that contains all data center, there are about few thousands of variables in the integer programming problem. Few thousands, yeah.
Let's do another question from the web. How does SPANStore deal with skewed item popularity, which is the case for content in social networks?
Okay, so for that question, we can rely on the application to tell us where the access will be accessed. So when the object first uploaded, we can rely on the application to tell us who the other users might access the object. So if that knowledge is known, so the problem is so the objects will already propagate to the data centers to give a lower latencies. But if we don't know the access set, so there might be a lot of cost overhead to deal with that case.
Great, thank you.
Thank you.